right, so let's play with multiplication. So first thing we gotta figure out is what's the meaning of multiplication. So what I want you to do is just think of a very simple multiplication problem and then come up with what is it? Why is the answer what it is? So simple multiplication problem, why is the answer what you think it is? Write down the problem, write down the answer, and you either draw a picture to illustrate it or explain why that answer has to be right. So a couple of common ones I think about for multiplication is multiplication is repeated addition. That's a pretty common one. So this would mean I have 3 2's added. So that means I have a 2, and I have another 2, and I have another 2. Whatever that adds up to is the answer. So 2, 4, 6, the answer's gotta be 6. Why? Because I believe multiplication is repeated addition. Anybody want to volunteer their example and meaning?
I had 2 times 3 as well. So.
Okay, and how did you illustrate? How did you explain it?
I did little blocks, 2
Okay.
groups of 3 blocks.
So you had 2 times 3?
Yeah.
And then you did 2 groups of 3 blocks? 2 groups of 3. So, whoops, 2 groups of 3. So here's 1 group of 3. Here's another group of 3. Right? All together, you have 6. Cool. Now, that's slightly different than mine. So if I use your groups of interpretation, I'm just going to redraw that. 2. I'm going to shrink this down. Get it all out. All right. So alternatively, I had written down not 2 times 3, but 3 times 2. And so I would look at that as 3 groups of 2, right? So I have a group of 2, and I have another group of 2, and I have another group of 2, and all together in all 3 groups, I can get my 6. So modeling it physically, is 2 times 3 the same as 3 times 2? The answer is no, they're different, right? Here I have 2 groups, here I have 3 groups, not the same thing. 2 groups is not the same as 3 groups. So modeling-wise, physically, addition really isn't commutative. The commutativity just refers, I get the same sum at the end, right? When I count them up. And we talked about addition means to combine and count, right? So I get the same count, but it's a pretty different picture when I change the order of it. Did everyone pretty much do a groups of kind of example when they drew theirs? Okay. So, so this gives us 2 models for multiplication. So let's go back here, add a new page. So multiplication models. Oops, models. And at the moment, we're just working on whole numbers. We'll worry about the other kinds of numbers later. One is repeated addition, and this is no special order. Two, a model is multiplication means groups of. Literally, you just replace the symbol with the phrase groups of, and out pops an answer. So somebody says, well, what's multiplication? Oh, it's timesing things. What the heck does times mean? Oh, it means groups of. What do you mean it means groups of? Yeah, like, you know, 2 groups of 3. Because then I can show somebody, you know, here's my 2 groups of 3. There's one, there's the other. The answer's got to be 6. Okay, so we can get physical with it. All right, my favorite model is actually neither of these. It's the area model. So with the area model, areas I like to think of as a base and a height. And the area is the base times the height. And the reason I kind of like base and height better is when we talk about length and width, I usually want length to be the longer one. So if this was my rectangle here, I want that guy to be the length. If this were my rectangle over here, I'd want that one to be the length, right? And then obviously this would be the width. But it could go either way, couldn't it? Right? I mean, I could call this the length and that the width. So I like base and height because whether I'm drawing on my, oops, I missed. Whether I'm drawing on my paper or on a board like this, there you go. The base is at the bottom and the height comes up from that. But you can do it any way you want. That just feels good to me. And then the area is going to be everything inside. And so with the area model, let's say I'm looking at 3 times 2. So I would say my base is 3. So I would measure off 3 units across the base. And then from there, I would measure up whatever the height is. And here my height is 2. And then that gives me this nice grid. The grid is then broken up into a bunch of squares, which then illustrate what the answer has to be, 6 squares. So for visualization, for me, this was always a big one. Rather than, you know, a group of 3 things in some random assortment, I have nice rows and columns. And some kids like that nice neatness to it. I was one of those kids. And so I just like areas. I think they're nice. But this model is going to be nice when we move on to talking about other kinds of numbers like fractions and decimals. We'll have an easier time explaining what multiplication means than, say, the group size model or the repeated addition model. We'll see that later. So there's another model that's kind of similar to the area model. Depends on your point of view whether you really believe it's different. It's called the array model. Does anybody happen to know what an array is off the top of their head? Hot takers on that one. An array is just a grid of stuff. So, for example, to show 3 times 2 for the array model, it's kind of like working with sets, but I have things line up really nice. So in terms of lining them up, there's nice rows and there's nice columns. Okay. So where the area model looks at the space in between, The array model only looks at those points of intersection. That's what we care about. The array model in math is what's known as a discrete model. And the area model is what's known as a continuous model. Like painting something, that's a continuous flow of the paint. Whereas area, these are arrays, these are like individuals in a seating chart. Okay, so discrete just means countable. I can't really count the paint on the wall, that's kind of weird. I can measure the volume of paint and it has a certain thickness, but it's just a different idea. So discrete just means counting. So the idea of discrete and the continuous make them different models, but it's pretty much the same idea. You have nice rows and columns. Whether you consider the intersections for the array model or the space for the area model. We stumbled across another multiplication model. We'll call this model number 5. Back when we were doing problem solving and playing with sets, the official name, it's got a couple of different names. One name is the Cartesian Product. And I don't think I spelled that right. Let's see. Yeah, oh, I guess I did. Cartesian Product. When we saw it back in chapters 1 and 2, I called it the counting principle. Or I might have called it the fundamental law of counting. That's another name for it. And what it's about, what are we counting here, is we're counting options. So suppose we want to buy a car, and the car comes in 3 colors. And then it's either 2-wheel drive or it's 4-wheel drive. So those are the only options this car has. Okay. How many different versions of this car are there? And so we could draw a picture of it in a couple of ways. One thing is we could draw a tree illustrating the colors. And maybe the car comes in red, blue, and yellow. And then the red car, well, that could either be 2-wheel drive or 4-wheel drive. The blue car could either be 2-wheel drive or 4-wheel drive. And the yellow car could be 2-wheel drive or 4-wheel drive. And so altogether, I get a bunch of different options in the end. So I can have a red car that's 2-wheel drive or a red car that's 4-wheel drive. I can have a blue car that's 2-wheel drive or a blue car that's 4-wheel drive. And all I do is follow the paths through the tree to get the final options. Finally, I could have a yellow 2-wheel drive car or a yellow 4-wheel drive car. And so I can see in the end, if I have 3 options for color and 2 options for the drivetrain, I get 1, 2, 3, 4, 5, 6 different possible cars at the end. And that was that fundamental counting idea that we talked about back in chapters 1 and then again in chapter 2. In chapter 3, they're calling it the Cartesian Product. It's cool, not as cool as the area model. So we'll come back to the area model in just a moment when we look at activity 3. Before we do that, I want to talk about some algorithms a little bit, and then we'll set loose to play. And then next class on Wednesday, we'll review multiplication and go over division stuff. And so when we put the multiplication and division together, we'll talk about properties the 2 of them have, kind of like addition and subtraction have all those properties. And we'll look at some more algorithms and models for division. So let's see. new page. So we'll come back to models in a minute. Let's take a look at algorithms, multiplication algorithms. So if you could take 23 times 24, come up with an answer right down there, you would do it without a calculator. So we all have a standard way of doing it, and my guess is we all do it exactly the same way. We would take 3 times 4 and make a note that's 12, but we would carry the 10 up and write the 1s down below, right? And then we would say 4 times 2 is 8, plus 1 is 9. And that's a place kids really struggle with when they first start this. Do I multiply and then add, or do I add and then multiply? Right? That's a complicated sequence of events. What happens next in this algorithm?
You would put a 0 down as a placeholder.
Yeah, put a 0 down as a placeholder. And that's taught differently in different places. And with some teachers, they just say, you know, leave that blank and just come over under the 9. 2 times 3 is 6, and they leave that blank. For messy kids, that's a disaster. Other places, they say, put an X there. Why put an X there? That's kind of weird. Yeah, I think 0 is the best option. We'll talk about why some more in a moment. Okay. So then 2 times 3 is 6, nothing to carry. And then 2 times 2 is 4. And so that goes there. And then I just kind of reconcile this. 5, 1, so 5, 25, or 5, sorry, 52. That we get. Okay. So just going to look at it a slightly different way. So another way to do this is just think about place value. 3 times 4 is 12, and for a long time they were just doing single-digit facts and they just wrote the answer underneath, so they're used to doing that. And even though they're starting to learn this carrying thing, and they did it with addition, they're gonna whip through it and they're gonna occasionally write that down by mistake. Okay? And then how do they proceed from there? Some kids will realize they made a mistake, they'll erase that 1, and they'll pick up, but other kids are gonna get confused at that point. But it turns out you can just go with it. So we take our 4 times 3. Next thing is we take the 4 times 2, but we know that's not really a 2 right there. What is it really? It's a 20. 4 20s. They've played a lot with this earlier. They know, oh yeah, that's 80. And you can just write the 80 right there. 4 20s is 80. Now, the more place values we have, the harder this gets to think about, but it just uses place value. Then I shift over to this 2 now on the bottom, because I've exhausted what I can do with the 4 1s. That's really not a 2, it's a what? It's a 20, and 20 times 3, or 3 20s, is what?
6.
Yeah, it's literally a 60, so we can just throw a 60 down there. And then, what is this? This is 20 groups of 20. That's a hard one. Well, we can reason through it. What do you think of this?
400.
It is 400. And an easy way to work through that is we know 2 times 2 is 4. We have to consider that we have those 2 place values to fill in. So it's not that bad. And then we reconcile the sum. We bring the 2 down. 8 and 1 is 9, and 6 is 15. And 1 and 4 is 5, so we get the same answer there. Okay. So we're going to call this the standard algorithm. In activity, let's see, 3, 4, 5. I think it's activity 6. We'll explore why that algorithm works the way it does. It's related to this idea here, which is called the expanded algorithm. So I don't think we'll get to that today, but next class we'll draw pictures of how the expanded and standard algorithms are related. Okay. All right, let's pick another algorithm. Let's see. I think we'll wait till next class to do the Hindu. So guess how the Hindu multiplication would work? Left to right, top to bottom. Yeah. So that's kind of weird, because then we're going to have to, you know, carry things down, which is interesting. So that's kind of mind-blowing. It's getting toward the end of class. I'll wait till you're fresh next time. This one always blew my mind. This one's called the Russian algorithm. Actually, do I want to do the Russian next? No, I'm not going to do the Russian next. I'm going to do the Lattice. Oops, what did I do? Come on. Hold on. Let's do Lattice first, then we'll do Russian. Then we'll play with a couple of activities. So the Lattice algorithm is cute. Let's see, what numbers? We were just doing 20, 23, 24? I think so. So what you do is, so normally, you know, sometimes you'll see a problem and it'll come like this, 23 times 24. And then we're taught to stack the numbers. Well, instead of stacking, and what you can do is you can kind of make a wraparound box type thing. So you write your 23, and then you go times, and then you write your 24 coming down like that. What that lets us do is create a box inside there. And then each number needs, for the 23, a column, and for 24, needs its own row. And then what I do is from the times, so coming from the upper right to the lower left, I put diagonals through each box. So there's my lattice. So I'm going to start down here in the bottom. This box right here is 3 times 4, which is 12. And the lattice is kind of set up for me to write my 12 like that. So the upper part of each triangle is the 10s and the lower part's the 1s. So 3 times 2 is 6. The 6 would have to go right there. 2 times 2 is 4. The 4 has to go there because it's 1s. And then 4 times 2 is 8. The 8 has to go there. Now the cool thing about the lattice is not only does the lattice have rows and columns, but it's got diagonals coming through. So we just follow each diagonal and see what happens. Let's switch to blue again. This diagonal right here, there's only a 2. And this one right here, it's 6 and 1, which is 7, plus 8 is 15. Carry the 1 up here anywhere. 1 and 4 is 5. And so here's my answer, 552.
It doesn't really matter where you start, does it?
Whether you, no, you can go anywhere. You can bounce all around the rectangle when you're doing it. No. So I don't have to start down here. I can start there, anywhere you want. Bottom line is at the end, you just follow each diagonal to get the answer. And that's called the lattice algorithm. And that's taught in a lot of South American countries. They do that instead of what we do. And I think that one's a pretty cool one. Okay, let's do the Russian one next, and then we'll play with activity 3. So the Russian one is all about halves and doubles. So you have 2 numbers you want to multiply. One number goes in the halves column, the other number goes in the doubles column. It doesn't matter which goes where. So I'm going to pick for the halves column 23, and then the 24 has to go in the doubles column. So what you do is you take half of 23 and ignore any remainders. So if I ignore the remainder, what's half of 23? 11, yep. So I'm going to call that 11. Every time you make a half, you come over to this column and double the number that's there. So if I double 24, I'm going to get 48. And I have 11, ignoring the remainder. That would be what? 5, yeah, it would be 5. 2 goes to 11 5 times with 1 left over. Who cares about the remainder? All right, since I have another half here, I have to get a double over here, so I double 48. That's 96. Cutting 5 in half. 2, yep, ignoring the remainder, it is 2. That means we have to double that 96 over here to get a partner. And that's going to be 192, I think. Cutting 2 in half, we get 1, and sometimes it just works out nice. And over here, doubling 192, we get 384 maybe? Okay. Now, once we get to 1, there's no point cutting stuff in half again because we were chucking the remainder. So there's nothing left to do. So then what I do is every time I have an odd number in the half column, the corresponding double is an important one. So 1 is odd, so I circle the 384. 2 is even, I don't care about 192. 5 is odd, so I do care about 96. 11 is odd, so I do care about 48. 23 is odd, so I do care about 24. So anytime there's an odd number in the halves column, I need the corresponding double. Add up those doubles and see what you get. Oh, I made a mistake. Oh, that adds up to 15, not 25. So I get 552, which is what I had before. Isn't that bizarre? How could this possibly work? And here's the weird thing. It doesn't matter if you switch which number gets doubled and which one gets halved. So I'm just going to do it again, switching them. So let's, for the halves, start with 24. And for the doubles, 23 would have to start that column. So half of 24 is 12, right? Double 23, and I get 46. Half of 12, 6, pretty nice. Doubling 46, 92, is that right? Half of 6 is 3. I double 92, I get 184. Half of 3 would be 1, because we have to ditch the remainder. Yeah, good. And then doubling 184, let's see, that would be 8, 6, 3, 68. Okay. Anybody remember the rule for when I want to pick a double? Yeah, if it's an odd half, so here I have an odd half, here I have an odd half, those are the only two. So if I add up those two numbers, what do I get? 4 and 8 is 12, carry the 1, 14, 15, carry the 1, I get 552. Isn't that the bizarrest thing ever? The craziest thing is people came up with this centuries ago. This is how they multiplied. Okay. I'm not going to go into why it works. It's very strange why it works. Obviously, it does work, and it doesn't matter like which one you're doing the halving and doubling to. You're going to get the right answer. Sometimes one way is easier. Like this one seemed a little easier than this one right here. Okay. Because here I had a lot of remainders to ditch. I don't know. And I had more numbers to add up. Sometimes it's like they're both just as hard. You know, it just kind of depends on the numbers. That's kind of weird. This is the way people have been doing math for years. It evolved in Russia somewhere. Sometimes it's called the Russian peasant method for multiplying. But all over the world, people have been multiplying, not necessarily the same way, but getting all the same answer. Just kind of cool. So I wouldn't show this to little kids that are just learning to multiply, because this would just like kind of blow away. But maybe I'll get some kids in my class that like are doing everything and they're bored. Maybe I'll give them this to kind of let them play around and, you know, to learn something new. So I'm not wasting their time. All right, let's take a look at some activities. So where are the activities? So multiplication arrays, this one is pretty straightforward and pretty quick. This uses, depending on your perspective, either the array model or the area model. And we're just going to make arrays for having 4 as the width or the base of every array. And then we'll have a 1x4 and a 2x4 and a 3x4 and so on. And we're going to take that all the way up to 10x4. And so if you didn't grab a piece of graph paper, it would be a good thing to have. Anybody need a piece of graph paper? So grab a couple. Need some, we did. We got some. Okay. We got some. All right.
Thank you.
So the interesting thing about the models we talked about, whether it's the groups of model or the array model or the area model, they're all related in a sense, right? Because they're all multiplication. But you can always boil them back down to repeated addition. Because here I always have rows of 4, right? So I'm just repeatedly adding 4 as I keep making these arrays bigger and bigger. Okay, so this is kind of playing around with that idea. And then what if we change the direction of the arrays? So at first, we're always having a base of 4. What if we make the height 4 all the time instead? Now we know, because we're very familiar with multiplication, what's going to happen. But young kids, this is going to be a discovery for them. Like, oh my gosh, it doesn't matter whether I consider a 3x4 rectangle or a 4x3. I still have 12 things in there when I do it. And so this is just getting used to drawing that out. So draw a few of these arrays to get it started, and then we'll talk about the next activity.